All right, welcome to section 2.3, calculating limits using the limit laws. All right, in this section, we use the following properties of limits called the limit laws to calculate limits. These are extremely important for you to learn and understand. They're actually pretty easy once we go through them, but they are important to know. All right, so limit laws. Suppose that C is a constant and the limits, so the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. All right, if those things are true, then we have these limit laws. So they look very complicated, but the reality is they're saying if you want to take the limit of the sum of two functions, simply take the limit of each individual function, then add them together. Okay? Nice and easy, right? That's all you got to do. Of course, this one's the same thing as number one, except subtraction this time. Just be careful, of course, in subtraction, order matters. All right, number three, right? So the limit as x approaches a. So this means of a constant times a function. So some number times a function is the same thing as taking the limit of the function, then multiplying by that same constant separately. Okay? All right. Number four. So the limit as x approaches a of the product of two functions, just like the addition and subtraction, you can take the individual limits and then multiply them together. Okay? And very similar with division, but of course, just like subtraction, order matters. And of course, when we have a denominator, that limit, of course, in this case, cannot equal 0. Otherwise, you have an undefined answer. Okay? So those are important. Make sure you learn these. Don't just memorize them, understand them. But, they're pretty easy. All right, so these 5 laws can be stated verbally as follows. So the sum law, the limit of a sum is the sum of the limits. Right? And the other ones are very similar. The limit of a difference is the difference of the limits. Constant multiple, the limit of a constant times a function, is the constant times the limit of the function. Product law, the limit of a product is the product of the limits. Quotient law, very similar. Just make sure that your denominator is not equal to 0. Okay? All right, so for example, if f of x is close to L, right? So if the limit is L and g of x is close to m, another limit, it's reasonable to conclude that f of x plus g of x is close to the sum of those two limits. All right, so here's a couple of examples. So let's go through these. All right, so we want to find the limit as x approaches -2 of f of x plus 5 times g of x. Okay, so it's kind of hard to do that graphically, but we can use those limit laws to break it into pieces. So I know I didn't leave much room. I apologize for that, but we'll write it out. So we're going to do the limit as x approaches -2, and make sure every single time, every step of the way, you got to write the limit as x approaches whatever, the limit as x approaches whatever. You have to keep writing it every single time. If you don't, then you definitely lose points because it wouldn't be mathematically appropriate. So limit as x approaches to -2 of f of x plus, and we'll use the constant multiple rule here. So we'll say plus 5 times the limit as x approaches, I can't write, -2 of g of x. Okay? All right, and so we'll find all the pieces here. So let's see. Limit as x approaches -2. So here is -2 on the x-axis. F is the pink function, so we follow from both sides. Remember that rule? The limit must be equal from both sides. Well, we can clearly see that limit is 1. All right, because it's the same from both sides. Let's see, so plus 5 times whatever the limit as x approaches -2 is for g of x. So g of x is the blue line. Well, that one's pretty easy. There and there. Oops. we can see that's approaching -1. Oh, there we go, -1. Okay. All right. So then we just put it all together. So 1 plus 5 times -1, that's 1 minus 5, which is -4. So what that means by the limit laws, this limit as x approaches -2 of f plus 5 times g is -4. Okay. All right, let's do part B. Clean this up. Okay. All right, the limit as x approaches 1 of f of x times g of x, so we'll use the multiple, the product rule. So limit as x approaches 1 of f of x times limit as x approaches 1 of g of x. Notice I'm not being lazy with my notation, right? You got to keep writing it out every single time. I know it's a pain, but that's the way this works. All right, so this is going to be equal to, so the limit, so here's 1. So for f of x, follow the curve there and there. We're going both sides of 1. Definitely that's a 2. So that equals 2 times. Now we look at the limit for g as x approaches 1 from both sides. So we're going down here and we get, what, a -1 here. And then as we come in from the left, we have a -2. Problem is we have that rule that says the limit must be equal from both sides for the limit to exist. So 2 times, and this is not, of course, appropriate, right? Can't say 2 times something that does not exist, but it's for notation purposes. So 2 times something that does not exist, therefore this entire limit does not exist. Okay? All right, that's important. Okay. And actually, we can kind of already see the answer coming up for part C. It's actually the same thing. We're just dividing now. So limit laws say limit as x approaches 1 of f of x over limit as x approaches 1 of g of x. Again, make sure you write limit as x approaches whatever every single step of the way. It's got to be in there. Otherwise, you don't get full credit for it because it's not mathematically appropriate. All right, so we already found the limit as x approaches 1 of f of x, and that's a 2. G of x at 1 does not exist. Again, this is not technically appropriate mathematical statement. It's just notation at this point. So we know this entire limit does not exist. Okay? All right. All right, so if we use that product law repeatedly, right? So we just use the product law in part B. We also have this new rule. Okay, this is another one to know. You need to know every rule we go over today. All right, so the limit as x approaches a of some function to a power, right? The shortcut is, the easier way to do it is find the limit of the function first. Take that answer and take it to the power of n. Okay, that's important. Let's see, number 7, another one. Limit as x approaches a of a constant is that constant. Nice and easy, right? Let's graph that one and see how that one works out. All right, so pick a constant here. I've got a constant function right there. All right, so let's call that c. And here's some a value. So we follow the curve. As we approach a from the left and as we approach a from the right, actually no matter where a is, right, the answer is still going to be that constant value. Okay, so that one's important to know. Number 8, the limit as x approaches a of the function x equals a. And you're like, what the heck? How did that happen? Well, again, let's graph it. So here we go. There's a graph. So x equals a. That's a line, right? I'm sorry. Y equals x, or f of x equals x. That's the function we're graphing here. That's a slope of 1 with an intercept of 0, y-intercept of 0. So it's a 45-degree line, right? Okay, so pick any A value. Doesn't matter where you pick it. Here's A. Well, we know this coordinate right here is A comma A, right? So as we approach A from the left and from the right, same thing happens to f of x or y. Okay? So either way, every point on this line is A comma A. So there you go. Another important one to know. Let's see. So if we now put f of x equals x into law 6 and use law 8, so here we go, 6 and 8, so it's using the exponent rule, we get this one, right? So it's the same thing as just simply saying, take that limit, well, which we know by rule number 8 is a, and we get a to the n. Okay, so another important one. Of course, 9 and 10 are actually the same rule, right? Because radicals can be rewritten, right? So the nth root of x can be rewritten as x to the 1 over n power, right? Remember, fraction exponents are radicals, so that's actually just an application of rule 9. No different. Okay? All right, and then we have the root law, which is very similar to what we just did again. The limit as x approaches a of the nth root of an entire function. It's just saying here, find the limit of the function, then take it to the nth root. That's it. Nice and easy. Okay, so you're going to learn all those rules, all 11 of them. You're going to know them. And it's going to make life so much easier. Because if you don't have a graphing device to do this limit is a little bit of a pain, unless you know some other tricks. But like I said, we'll go over that stuff later. All right, so anyway, we're going to use all these different rules we just learned. Okay, so again, notice, look, equal signs, right? Don't forget your equal signs. Some people got knocked off on the review and the exam. You got to have equal signs. That's part of math. All right, so we're going to write the limit. Actually, my mistake, because we have a constant here, don't we? So we're going to use the constant rule, exponent rule, subtraction rule, constant multiple rule, addition rule. Lots of rules here, right? Welcome to life. All right, oops, did it again. So we have a 2 out in front, 2 times the limit as x approaches 5 of x squared, right? Okay, minus 3 times the limit as x approaches 5 of the function x plus the limit as x approaches 5 of the constant function 4. Oh yeah, so constant rule there. Okay, so now we just find all the parts. So here we go, let's see, 2 times something squared. So we have a rule that says for the limit as x approaches 5 of the function x, the answer is the a value, 5, right? Okay, minus 3 times, well, we just found this value, didn't we? It's 5. Plus, and then we have the constant rule, that's a horizontal line at 4, so no matter what, 4. So put all this together, use PEMDAS, right? So this is 2 times 25 minus 15 plus 4, which should be 39. So 39 is the limit as x approaches 5 of that function right there. And you'll see later on, of course, that's our function in this case is a polynomial. Polynomials are are consistent everywhere, or continuous everywhere. So we'll be just allowed to plug in, but we'll talk about that later. For now, show your steps, practice these limit laws. Okay. All right, now B, it's going to be a mess, but it's part of the learning process, right? Okay. So I'm just going to kind of go over this one a little bit quickly. We're going to use all the different rules, exponent rules, constant rules, adding, subtracting, multiplying, all that stuff, okay? So we're going to the limit as x approaches 5 of x cubed plus 2 times limit as x approaches 5 of the function x squared minus the limit as x approaches 5 of the constant function 1 over limit x approaches 5 of the constant function 5 minus 3 times the limit as x approaches 5 of the function, of the function x. There we go. Okay. So the limit as x approaches 5 of the function x is that a value 5, right? So 5 cubed plus 2 times 5 squared minus, right, that's the limit of a constant function. It's the constant. This is a constant 5 minus 3 times. Limit of the x is 5. All right, and then of course you can do your PEMDAS. Make sure you use PEMDAS, very important. All right, so just to show it, let's see, 125 plus 50 minus 1 over, 5 minus 15, which is negative 174 over 10. And again, just so you know, you don't have to draw these arrows, I'm just showing you. That answer is the limit of that entire function. Okay? All right, now I was saying before in part A, well, that, part A, this function is a polynomial, right? Polynomials are continuous everywhere. We can have this rule and this rule. It's like a million stars, right? Super, ridiculously, incredibly important that you know this rule. You're going to hear me quote it so many times throughout this chapter. You're going to get so annoyed with it, but you're going to know it. All right, the direct substitution property. So guess what we're going to do? We're going to substitute, right? So here's the deal. If your function, so this function that you're trying to find the limit for, if it's a polynomial or a rational function, and a, so this little value a, if a is in the domain of your function, then you simply plug in. Okay? And we'll see later, functions with the direct substitution property are called continuous at that a value. That's a definition we'll talk about much later, a little bit later. Okay, so let's apply this rule. So here we go. Example 3. So when we use this direct substitution rule, we're going to ask ourselves 2 questions every single time. Okay, well, every time you take a limit from this point on, you should ask yourself 2 questions. Ask yourself, is the function a polynomial or rational? If it's one of those 2, then ask yourself, is a in the domain of this function? If both answers are yes, you plug in. It's nice and easy. Okay? All right, so this is a rational function, right? Ratio, fraction. All right, so this is rational. So that's question number 1. The answer is yes, it's rational. Is 5 in the domain? In other words, if we plug a 5 in for x, do we get a 0? No, we don't get a 0, so yes, 5 is in the domain. So this is nice and easy. We simply plug in. Right, now notice here, I did not write limit as x approaches 5, right? Once you use the direct substitution rule, once you plug in the numbers, you no longer use the limit notation because it's not a limit anymore. It's simply, that's the answer, right? All right, of course, we'll calculate it. What is that? 25 minus 1 is 24. 5 minus 1 is 4, so I believe that's a 6. Okay, and again, 6 is the limit as x approaches 5 of that function. Okay, so again, we're going to ask ourselves those 2 questions. Is our function a polynomial or rational? If yes to either one, is a in the domain of that function? If the answer is yes again, got to have 2 yeses on that one, then the answer is you plug in. Nice and easy. Okay, so here's another rule. If f of x equals g of x when x is not equal to a, then the limit as x approaches a of f of x equals the limit as x approaches a of g of x, provided the limits exist. What does that even mean, right? I think that's just mathematicians from, way back when they made this stuff up, trying to make themselves feel important because no one else understands what the heck they're saying. But anyway, that's just my opinion. All this is saying is you're allowed to reduce your functions, right? This is a function, rational function. Actually, same one we just did, right? So we actually already know the answer. But this is just another way, actually, a little bit of an easier way to do this one. Okay? All right, so let's simplify this fraction. So we haven't plugged in yet. So we still have to write limit as x approaches 5. This numerator, remember back to your algebra days, right? Sorry, don't mean to bring up any PTSD, but your algebra days should have reminded you here that that's a difference of two squares, right? A square minus a square. So that one's easy to factor. That's going to be x plus 1, x minus 1. Of course, the plus and the minus doesn't matter, the order here, over x minus 1. So we can, don't say cancel, say reduce, right? Cancel means goes away. Reduce means simplifies, okay? So now we have, and again, equal signs and limit notation. The limit as x approaches 5 of x plus 1. So we ask ourselves the question, is this function a rational or a polynomial? It's a polynomial, right? So is 5 in the domain of this polynomial? Well, hopefully you know any polynomial, the domain is all real numbers. So if you have a polynomial, you're already guaranteed you can plug in. All right, so we're plugging in, so we drop the limit notation. It's going to be 5 plus 1, which is 6, which, yeah, we knew that. But again, it's just a different way to do it. Remember, in calculus, you're going to learn to do things in different ways, all right? Ways you may have never seen before, but just, make life easy on yourself. That's what this class is supposed to be. Well, I know the homework's a lot, but you know what I mean. All right, moving on. Let's see, some limits are best calculated by first finding the left and right hand limits. The following theorem says that a two-sided limit exists if and only if both of the one-sided limits exist and are equal. We've already talked about this one, but again, it's got to be said again. So if the limit from the left equals the limit from the right, and they exist, of course, and are equal, then the limit exists at that a value. And remember, if and only if, remember this statement is valid in both directions. Okay? All right, so example 5 here. We're going to prove that the limit as x approaches 0 of absolute value of x over x does not exist. So there's a nice little hint right there. Find the limit as x approaches 0 from the left and from the right. Okay, so first thing we've got to talk about, or maybe remember, I think I may have talked about this. Yeah, I think we talked about this in chapter 1. But the piecewise definition of absolute value of x. Remember, it's x if x is greater than or equal to 0, but it's negative x if x is less than 0. Because if x is less than 0, then x is negative. So negative x means negative negative, which means positive, right? Okay, so using that and using this and using our newfound knowledge of limits and limit laws, let's figure out the limit from the left and the right as x approaches 0. So in other words, limit as x approaches 0 from the left of, so from the left, that's this piece of the piecewise definition, right? To the left of 0 are negative values. So we'll do negative x over x. So we ask ourselves the two questions. Is this polynomial or rational? Well, it's rational, but what's the problem here? 0 is not in the domain, right? If we plug in a 0, we get a 0 in the denominator. That's not 0, it is undefined. Okay, so we cannot just plug in. So we use the other rule we just learned up here, simplify. Negative x over x is the limit as x approaches 0 from the left of the constant function negative 1. We know that rule. That means the limit is negative 1. Okay? All right, so that's the limit as x approaches 0 from the left. Let's do the limit as x approaches 0 from the right. From the right of 0 means positive, right? So we're going to use the top part of the piecewise defined function, so x over x. Again, we ask ourselves the questions, is this function a polynomial or rational? So yes, it's rational, but again, if we plug in a 0, 0 is not in the domain. We'll get a 0 in our denominator. So we simplify. Keep the limit notation going. Oops, not an x, that's a plus. There we go. Of the constant function 1, which equals 1. So we have a problem here. From the left, the limit is negative 1. From the right, the limit is 1. Based on this theorem, we just learned the limit does not exist. Okay? And again, when you're doing work in calculus, you've got to show your work. You cannot just put an answer down and expect to get full credit. Actually, all you'll get is maybe 1 or 2 points for the answer, and that's it. You'll lose all the rest of the work, all the points other than that. Okay, so always, 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 always show your work. Okay, moving on here. Let's see, when computing one-sided limits, we use the fact that the limit laws also hold for one-sided limits. The next two theorems give two additional properties of limits. These are important as well. So if f of x is less than or equal to g of x when x is near a, except possibly at a, we keep hearing that statement, right? Remember, for limits, we're not concerning ourselves with what's happening at x equals a, just near on both sides. And the limits of f and g both exist as x approaches a, then that just simply means the limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x. All right, so it's just like applying, the limit to both sides of your inequality here. That's all it is. That's the easy way to remember it. Okay. Then we have this thing called the squeeze theorem, which is it Calc 3 or something like that? You'll prove. Yeah, it's horrible, but you'll do it. So this is just kind of an extension of number 2 up there. But if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a except possibly at a, and the limit for f and h, in other words, the two outer functions, if they're equal at L, that means the guy in the middle, g, his limit at a is also L. In other words, that limit gets squeezed in between. It has nowhere else to go. Okay? All right, so here's the visual of the squeeze theorem. Right, so we see at x equals a, we've got h, well, let's just say g is between h and f, right? We can agree on that. And we can agree that if we check the limit of h and f from both sides, it is definitely L. Well, g is sandwiched in between there. It's squeezed in between h and f. It has nowhere to go. So its limit at a also has to be L. Okay, that's an important one to understand. Okay, let's use an application of this. So, of course, this is actually a shortcut. I know it seems confusing, but the squeeze theorem is a shortcut. So here's an example. So we want to show that this limit, so here we're taking the limit of this nasty function here. Limit as x approaches 0 of x squared times sine of 1 over x equals 0. So the problem is it's not a polynomial. Well, part of it's rational, but if we plug in a 0, it's not in the domain, right? We'd get 1 over 0. So we can't plug in. So we got to do some fancy footwork here. All right, so what we're going to do is we're going to use the multiplication rule, right? So we're going to break this up. So there's multiplication in between the x squared and the sine of 1 over x. So we break it into 2 pieces, all right? This limit we know is going to be 0, right? But we got to figure out this limit of sine of 1 over x, right? Oh, well, sorry, we're trying to find the limit of the entire thing. But we have a piece that does not exist and a piece that does exist. So we can't just do it with the algebraic means we have. We have to use the squeeze theorem. All right, so right here, we know that what they're saying is the value of sine of 1 over x is between -1 and 1. Why is that? The reason is simply the graph of sine. This is something you ought to know, and this is something we went over last chapter. So here's a sine wave, right? We know the period is 2 pi, but what we know is, since there's no coefficient in front of there, well, technically there's a 1, that means the amplitude is 1, which means the highest y value is +1, the lowest y value is -1. That's why we get that statement right there, where we know sine of 1 over x has to be between -1 and 1. Okay, so we're going to use that, and we're going to follow these directions here. So we have -1 less than or equal to sine of 1 over x less than or equal to 1. Now it's telling us multiply everything by x squared. Well, that's because that's what we're trying to figure out, right? The limit of that function. Okay, so our knowledge of inequality says, yeah, we're allowed to multiply everything through all three parts by x squared. So, x squared, x squared, x squared. There we go. Now we have that. We had another rule up here that says we're allowed to apply the limits to all the pieces. Where did it go? Right here. Number 2. We're allowed to apply limits to inequalities. So this is what we're going to do. We're going to take the limit of each of these three pieces. So we'll take the limit. Oh, and what limit are we doing here? From up here. X approaches 0. So the limit as x approaches 0 of -x squared, that's less than or equal to the limit as x approaches 0 of x squared times sine of 1 over x, which is less than or equal to the limit as x approaches 0 of x squared. Okay, so we're going to apply limit laws. We know we have a constant multiple and an exponent. So we're going to use those two rules. In other words, we're just going to find what's the limit as x approaches 0 of the function x. 0, right? -0, 0, 0 squared is 0. Well, I kind of did that in the wrong order, but in this case it won't matter. Either way, the answer's 0. Okay? Less than or equal to that middle one. That's the one we're trying to figure out. We don't know it just yet, but, well, you can kind of see the answer coming up. Now we find the limit of this guy here. Limit as x approaches 0 of x squared. Well, we know the limit as x approaches 0 of x is 0. 0 squared is 0. So there it is. The function, so this inequality satisfies the squeeze theorem, right? Okay, so since we satisfied the squeeze theorem, since the two outer limits are 0, thus the limit as x approaches 0 of x squared times sine of 1 over x equals 0. And we have to say why. By the... I spelled that wrong. That's funny. Squeeze theorem. Okay? There you go. Write a little sentence. Right? Always use all your information. Be appropriate. Oh, I already had it written out. There it is. Thus, by the squeeze theorem, limit as x approaches 0 of x squared times sine of 1 over x equals 0. All right, and there you go. Thank you.